and the nitrogen would have remained. Okay, so here's our typical cutaway shot of the atmosphere of Titan, our familiar temperature curve. It's the same general shape that we see everywhere else. We pretty much always see a temperature that drops and then goes up. The only exception to that shape that we're seeing right there, that sort of check mark shape, is the Earth itself, which actually has an extra bump at a certain altitude because of the ozone layer where energy is absorbed. We don't see that in any other atmosphere. All of the other ones have a shape like this with minor changes in some of the details. But let's look at the temperatures and pressures. Now there's a solid surface on Titan, so we can actually talk about what's happening at the surface. And what we see is, my laser pointer just died on me. My laser pointer won't even work at these cold temperatures that we're talking about now. But the surface is less than 100 kelvins, only 97 kelvins. So again, outer solar system, distance from the sun increasing, you're getting into this incredibly cold region of the solar system. But surprisingly enough, the pressure is actually pretty high, 1.6 times Earth's surface pressure. The reddish color that we see due to this haze layer, which is probably mostly an ammonia haze up here in this orange part of the atmosphere. And again, there could be a methane-ethane rain cycle at these temperatures and pressures. That's actually part of the what we call the phase diagram, where you can have liquid methane and ethane. It's really, really cold, but it's high enough pressure that the gas can liquefy, as opposed to at very low pressure, it would just evaporate immediately into a gas. So if you think about, for example, water, if you think about temperature and pressure with water, there's a certain part of the temperature pressure space where you can have liquid water or gaseous water or solid water, ice, right? Well, this is a part of the phase space where you can actually get liquid ethane and methane at higher pressure. Just some shots looking along what we call the limb of the moon, the edge of the moon there. You see an atmospheric haze structure. Okay, so now we move on to chapter 13, which is what we're going to wrap up by 4 o'clock. It's that clock. I don't think I've gone that long. I think that clock never. Okay, so the outer planets, we're talking about Neptune, Uranus, and we still talk about Pluto. It's not technically a planet anymore. It doesn't really know that because sound waves don't propagate into the outer solar system, so we still kind of put it into this group here. In fact, as we'll see, Pluto is really more like a double planet because it has a moon, Charon, which is 1/6 of the mass of Pluto. 1/6. Now, if you remember, the Earth's moon is 1/80th of Earth's mass, and we said that was the mass of the moon relative to Earth, at 1/80th. Charon there is 1/6 of the mass of Pluto, so they're really comparable objects. So we sometimes think of it as a double system where we have orbits of the two orbiting around a common center of mass. Now, if you compare Neptune and Uranus with Saturn or Jupiter or even Titan that we just looked at, there's clearly a major difference just looking at these two guys. They're very blue. I mean, you would be too in the outer solar system. Internet reception is crap. I'm sorry, to use a vulgar term, but it's very boring in the outer solar system. There's not really much to do. We do see multiple moons around the outer planets, some significant major moons around them, which we'll talk about. Again, a variation of sort of inner types of moons, and then moons that are at a very large distance, kind of like Titan, which are a little harder to explain unless we think about a capsule type theory. All right, so this is again a little reunion that took place, hosted by the Earth, and we see the gas giants all lurking there. One funny thing about this, which just actually occurred to me, when we get past this next exam, we're going to talk about comets. It turns out that when comets get into the inner solar system and the cometary nucleus starts to sublimate and you get this big gaseous thing with the tail and all that stuff, the head of the comet actually turns out to be about the size of Saturn. So when a comet gets into the inner solar system, its coma, where the gaseous material forms off the ice, actually is comparable to that size. They're not generally, really threatening the Earth, like they're not really gearing at the Earth like Saturn is there. They don't get anywhere near as close, but I just felt like pointing that out because we see the scales next to each other. Anyway, the main point here is that Uranus and Neptune have the bluish color. They're giant planets, but they're smaller than Saturn and Jupiter. So as we work our way out into the outermost part of the outer solar system, we see a diminishment of size. the size maxed out at Jupiter, and then we're seeing diminishment after that. But we're also seeing changes in composition and density and temperature. Okay, so again, our roadmap here, when we get into the solar system beyond Saturn, now you're getting beyond 10 astronomical units from the sun. Now just to remind you in terms of the timing it takes for light to travel, it takes 8 minutes for light to reach us from the sun. So that we say the sun is 8 light minutes away. It takes 8 minutes for light to reach us from the sun at a distance of about 150 million kilometers. Now look here, Saturn at a distance of around 10 astronomical units means that when we look at Saturn, we're seeing it as it was about 80 minutes ago. But it gets much more extreme when we get farther out. Uranus out at 20 astronomical units, Neptune at 30, and Pluto at almost 40. When we see Pluto, we're seeing it as it was about 5 hours ago, roughly. Right? Do the math there. Densities in the outer region. Saturn's the minimum at 0.69, but we see that Uranus and Neptune have densities pretty similar to that of Jupiter. And then when we get to Pluto, we see a density of around 2 grams per cubic centimeter. Well, it's sort of similar to Neptune, let's say, but Pluto for sure is not a gas giant planet. It's a tiny little object. So Pluto actually is an icy object, a lot more like the icy moons of Saturn, for example, that we were just talking about a moment ago, that have densities around 2. So when you have a small body with a density of around 2 grams per cubic centimeter, that's an icy body. And when you have a giant planet with that density, it's probably a gaseous planet. Okay, so Uranus was discovered in 1781 by William Herschel. This is, of course, the pre-photographic era we're talking about. So what this means is that William Herschel would go out and he would study regions of the sky using a large telescope that he built, but there was no photographic comparison with anything else. So literally using memory, he was able to look at some region of the sky that he looked at the night before and notice that one of these points of light had moved. Okay? So this is just an amazing ability to be able to even remember a pattern like that. I think he could have made sketches before it, but it's still pretty amazing because he's scanning the whole sky and he notices that there's this body, this point of light, which is star-like, but it's not a star because it's moving relative to the background stars. And remember, the whole idea of a planet is planets are actually defined as things that move with respect to the background stars. So there's something else going on there. So he discovers Uranus in 1781. First new planet discovered in 2,000 years. We have to go all the way back to the primary 7 planets, the time of the ancient Greeks, to talk about the original planets. All right. You actually can see it without a telescope. It's a very borderline, bright object to see with the unaided eye. And of course, you can't see the disk or anything without a telescope. All right, so the distance that we're talking about varies by about 10% because the eccentricity is about 5%. So the distance variation is about 10%, and we can actually see that in the comparison of the perihelion and aphelion distances. When it's finally really dying, it usually responds to a gentle massage of the battery. But there we go. There's about a 10% variation, but again, look at the distances around 20 astronomical units out from the sun. Well, some people are allergic to the outer solar system. I've noticed that over the years, of course. Kepler's third law will relate the period to the semi-major axis in the usual way. Here we've set it up so that we can stick the period in on the right-hand side, and we get the semi-major axis. So with a period of 84 years, we find then that the semi-major axis is 19.2 astronomical units. Right between the perihelion and aphelion distances. Because remember that this semi-major axis is actually just the average of those two numbers up there, so between the perihelion and aphelion distances. But the amazing thing, of course, is the period is 84 years. I mean, it's a once-in-a-lifetime orbit at that distance out from the sun. Further analysis of the orbit of Uranus as it continued through its orbit turned out that over a period of 50 years, now mind you, 50 years is not even one orbit. Oh, he's dead. Just belched out his batteries, actually. Wow. Sorry, we just not even using any anesthetic. I'm just sticking the Okay. Well, so my point was that the orbit of Uranus is 84 years long. So in 50 years of following that orbit, it's not even one time around the sun, but nonetheless, there's an indication that it wasn't quite following the predicted path. There was actually a discrepancy that built up to about 15 arc seconds. It wasn't in the position predicted by propagating its position forward using Kepler's laws. So there was an issue with, was there something wrong with Kepler's laws in the outer solar system? Were they sort of only approximations that were breaking down in the outer solar system? Or is there another gravitational force at work which could be affecting Uranus's orbit? And that actually led to the discovery of Neptune, because in the mid-1800s, two mathematical physicists working independently deduced that the discrepancy in Uranus's orbit could be due to another massive body which is exerting a perturbing influence. It's kind of similar to what we saw when we looked at Jupiter's moons, and we saw that Europa was affecting the orbit of Io. These bodies interact with each other. So what we see, this is an interesting moment in the history of astronomy and mathematical physics, because when Neptune was discovered in 1846, close to the predicted location, the credit didn't even go to the astronomer who found it there. Nobody even remembers his name. The credit for the discovery actually went to the mathematicians who predicted it was going to be there. So it's kind of an interesting twist there. And so that was called Neptune, and of course has a similar coloration to Uranus. The eccentricity is very small. There's very little variation there's very little difference between the perihelion and aphelion distances in the case of Neptune. And again, we can use Kepler's third law. This time it's turned around the opposite way, so we can stick in the centimeter axis and compute the period. So the centimeter axis is the average of those two numbers up there. It turns out to be 30.1 astronomical units. When we do the math, we now obtain 164 years, just about twice as long as the orbit of Uranus. This isn't even once in a lifetime. This is multi-lifetime type of orbital timescale. So since 1846, it's just about completed one single orbit of the sun in that time period.